Hi everyone, this presentation is about the G3S capability of exhaustively searching for solution in a given search space, namely in a formula. And later on, during this presentation, I will show a number of real-world problems solved using this capability. So for now, I will show you what is the benchmark I am using today. And this benchmark actually is built out of two different benchmarks put together. So the AAM benchmark, there are files with 50 up to 200 variables each. And the specific of the AAM benchmark is the fact that each formula has only one solution, a unique solution within the given search space. Whereas the other benchmark is built out of 100 variables, 400 clauses, and has multiple solutions for each formula. So now let's run all of them and see how it goes. And it goes quick. Good. So as you can see, the order of execution complexity is quite low. It's polynomial, where n is the number of variables. So it's polynomial in terms of variables access or touch. So let's get one of them now and analyze how it works. So let's also print out its solution. As I said, number of solution in the AM benchmark is 1 for each file, for each formula, and this is the solution. Now I have here the concept of backbone. A backbone, it means represents a subset of immutable Boolean variables in terms of their polarity for any given solution. That means that the backbone elements will have the same polarity in any solution found. Now, since the backbone here is the same as the number of variables, it means that this subset, or actually set of booleans represent exactly the solution itself. Now let's see the difference versus the other one, and we'll do the same thing and see how many solutions we have here. So we have 432 solutions and a backbone of 90 elements. As you can see here, these are the backbone elements contained in the backbone. So now, if you look here now, formula number, what was that? Okay, 0 is having 432. Now, let's take another one. Now, this one has 122. And let's take a look inside the backbone and find one that actually does not belong to the backbone. If you can figure out one. Okay, 39, 40, and 41. It means those can have any polarity. For instance, this one here, 40, that's missing from the backbone, takes both polarities, right? Now 39 should be exactly the same. Yeah, negative polarity and positive polarity. So that's about it in terms of backbone and exhaustive search. Now, why is this useful? So, in order to present you the usefulness, I prepared 3 real-world examples, problems, so to speak. And the first one is a fairly simple classical transportation problem. So the story is the following. Suppose that we have 3 warehouses and 12 delivery points. And those are the distances between warehouses and delivery points. Now, there are 2 conditions here. Each warehouse should deliver at 4 delivery points. That's first condition. Second condition, each delivery point supposed to receive only once the merchandise. And obviously the objective, which is objective function, which is minimize the distance. Now this is an XLS file, and I have the CSV counterpart that I will be using as an input to G3S in order to optimize this and find the solution, the optimal solution for this transportation problem. And that is because obviously there is no UI attached to G3S algorithm yet. So let's use the counterpart and figure it out. And I will stop it after each step in order to explain what it means. Step 1, simply loading the CSV file, the data. Second is modeling, is transforming the mathematical model into a Boolean satisfiability model. And this is the new file that would be actually solved by the solver. And that file contains 36 variables and over 2400 clauses. Step 3 is objective function. G3S understood that we want to minimize the distance in that transportation problem. Step 4, solving the problem. Okay, so it found over 34,000 solutions, and the backbone is 0 elements. And it means that having that many solutions, one of them should be optimal. So let's map the best solution to the model itself. Okay, so here is the result. It looks to me that is warehouse 1 would send to DP2. Let's make it yellow, and all of them. And then DP6 and 11 and 12 and so on and so forth. So DP1, DP3, and D5 and 9 here. And probably the last one would cover for the rest, uncovered. Yeah, this and this. So of course, you could try this exercise by taking a snapshot of this screen and figure out whether this is the optimum or not, but because it should be fairly easy. But I can guarantee this is the optimum. Now, let's try another example in a different industry field, namely into protein design. So protein design, this is the story. We have a protein bar built out of 4 different proteins: whey, soy, casein, and pea. And we are trying to minimize its energy. We are trying to minimize the energy level. Now, by adding different amino acids to the structure of each individual protein. Adding an amino acid to a certain protein may add or remove some of its energy depending on the impact. This is represented by the values. The energy impact is represented by the values, the impact of the amino acid on the given protein. And the objective, as I said, is to minimize the energy level, lower the calories in my protein bar. And let's use its counterpart, its CSV counterpart, and try to see how it goes without stopping anymore. So it built a formula of 48 variables and over 2,000 clauses. And as you can see, it's taking a bit longer than the example before. And we'll see how it goes. And you'll see why it is taking that long. Why? Because that formula has almost 370,000 solutions. And we managed to have an impact of 30 calories. We could lower the number of calories in that protein bar. So let's try something different. Let's take the CSV and modify it. Okay, and instead of minimum, let's look for the maximum. How many calories could we add inside that? Let me change, not to forget on this one as well. How many calories can we add in the protein bar given this particular structure? Again, did the same thing as above, and obviously, given the conditions, has produced exactly the same number of variables and clauses, and solving and applying to the model and see what we can get as maximum energy addition to the protein bar. Okay, so we could add almost an extra of 370 calories. Okay, now if those two examples seem fairly simple, maybe you could also try it manually, although this is a bit harder, I would say, to solve it manually. And by the way, there are tools out there that will actually help you, but that's not the point. The point is to show how useful is the exhaustive search in the given condition, in the given model. And let me jump to a different example, and that is related to banking. And the story is the following. There is a bank that has 5 investment funds, where each investment fund has a different goal. So, for instance, Fund 1 has as goal a capital appreciation, then income generation, preservation of capital, and so on, so forth. And these are the investment types: investment in stocks, real estate, mutual funds, venture capital, equity, so on and so forth. And this table is related to the risk associated, estimated risk associated to each investment. Now, the second table is the investment amount. The investment amount that looks to that each fund has is allowed to invest in different areas, in different types of investments. And the last one is the estimated profit in case that amount, let's say for capital appreciation, this amount is invested, then this would be the profit. And then we have the conditions. Each investment fund should actually invest in 2 different types, and each type of investment is being used only once. The objective functions are the following. First table, to minimize the risk. Second, to minimize the investment. And obviously, the best of the world is of the 3 worlds is to maximize the estimated profit. And obviously, since there are different numbers here and not really correlated, we might obtain a different optimum. And we'll look at that as well very soon. So let's try to run this. Let me first check banking. Let's look at the CSV first and see whether it was maximum. Let's say we put minimum in order to be exactly mirror with the XLSX file. Okay, so let's do it, and we'll try then the other one. So G3S banking and see how it goes. So it built based on the constraints. Has built a formula with 50 variables and 700 clauses, over 700 clauses. And as I mentioned before, the optimums are different from table to table because there are different tables. So what to do about it? So the risk, the cumulative risk is this, and so on. That's the end result. Well, we will use something else. Let's open the CSV and let's take the top 10 results and try to align the results without influencing the risk. So let's do this. Where is that? This one. Now we have an extra constraint, which is not a constraint actually. It has to intersect the top 10 results from each table and try to find an optimum for all of them together. Now everything is aligned. You see? Every single table in that file is aligned. And that would be the estimated profit in this case. And also, interesting, the optimization of the risk was not affected. It's not higher than it used to be. So that is about it related to this presentation. And my next presentation will be about complexity decay, and I'll explain what that is in the next video. Until then, stay safe and goodbye.